All right. Hello, everyone. I'm Bernd, and today is day 17 of Advent of Code. And today we're playing Tetris. So what we're given is a few possible rock shapes. So like this is a line, then a plus sign, and so on. And then at each time, one of those rocks corresponding to the shape will drop. And it's like Tetris. It falls down, and at each step, it can either also move left or right, depending on jets of hot gas that push it left or right. And then it moves down until it hits the floor or another rock, and then it stops, and the next rock will drop. And then we do 2022 dropped 2022 rocks, and at the end we want to see how high the corresponding tower is. So how can we do that? So we have the number of drops, we have the width of the corresponding room, and then we'll also have the all rock drawing, so we'll pass it from there, and it saves us from putting in the numbers by hand or so. So in order to make things easier for us, we'll have this position class, and we can add to position by just adding the coordinates. And then from the rock drawings, we can get the rock. We define a function to get the rock shapes. So we split all rock drawings by an empty line, which will be 2 new line characters in a row. And then for each of those rock drawings, we get the rock shape corresponding to the drawing. How do we do that? We just go through all the lines in reverse in this case. Then we go through all the characters in the line. And if the character is equal to this number sign, it's part of the rock, and we'll add it the corresponding position to the rock shape, and then we'll return it. This allows us to get all the rock shapes corresponding to the 5 different kinds of rocks. And then we'll also have a class rock, which will be useful in doing for the code. So a rock is initialized by supplying a left edge, where the left edge is, the position of the bottom edge, as well as an index. And then we'll set the bottom left position, of course, from the left edge and the right bottom edge. And then the rock shape will be determined by the index, and it's just the 5 rocks are repeated in order, so it will just be the index modulo the length of the rock shapes. Okay, then it has a few properties such as width and the set of rock positions. So we have the shape, the rock shape, which just gives a few positions, and then we'll offset them by the bottom left in order to get the positions within the grid or within the room. We'll also have a few pushes, so the left and the right push and the corresponding positions we need to process the input, and we also add 2 more for convenience. And then in order to actually solve the problem, you of course need to read the file and split it into lines. And then a main function will be drop, so we'll drop a rock depending on the positions where they're covered with rock. We'll find the final position, and we'll update the core tower height, and we'll also require the pushes that will happen to the rock while it's dropping. So for that, we'll iterate, we'll have a loop, and we'll just consider the next push, and then we save the bottom left position of the rock, and then we add the push to the bottom left position, and then we check if the push was actually legal. So for example, if the left wall overlaps with the rock, or the right wall overlaps with the rock, or another rock overlaps with the rock, we cannot actually do the push, and the puzzle tells us then it's just ignore the push, so we reset the bottom left to the old bottom left position. And then we want to do the downwards move. So again, we save the bottom left position, and then we do a push corresponding to the downward, or we add the vector at the position corresponding to the downward push to the bottom left. Then we again check if that was illegal. So in particular, if the floor overlaps with the rock, or another rock overlaps with the rock, it's not possible to do this move. Then we reset the bottom left of the rock to the old bottom left, and it also means the rock cannot move down anymore, so it comes to a halt. And for each rock position of the rock, we'll add it to the covered positions, and then we also update the height of the tower. Okay, so all this helper function like left wall overlaps are fairly simple, so I'm not going to go through it. This is then already everything we need to solve the problem. So we'll have the pushes, which will consider of the 1 line we have, and the corresponding position, and we'll cycle through it, so we'll repeat it indefinitely. We'll keep track of the tower height, and we'll have a set of positions that are covered by rock. And then we just iterate and do for each drop we're supposed to do. we initialize a rock, so we are told that each rock is initialized such the left edge is at position 2, the bottom edge is at position tower height plus 3, and then we also give it the index that will determine the shape of the rock, and then we'll just drop the rock and update the tower height. And then this will give us the tower height in the end, which will be our solution. Okay, we can do a little test on the test input, and with a bit of luck, amazing, that works out. So we can also run it on the real input, and that works out as well. Okay, part 2, we have a few more drops, so it's infeasible to do that many drops, so we need to think of something smarter. So what we will do is we'll try to find a repetition where the same position repeats over and over again, and then we can make use of that and just calculate what the final position will be instead of simulating all the drops. So that we need a bit of a slightly more advanced push iterator. So we define that. So we have the line as the pushes, and we'll keep track of the push ID. And then whenever we call next, we'll just increment the push ID, return the corresponding push. But we'll also do one more thing. So we have this rolled over attribute. And if the push ID is equal to the length of the pushes, so we're like at the end and 1/3 at the end, we'll reset the push ID to 0. We need that to repeat. But we'll also set this rolled over to true so that we can react to this rollover where we went through a line once. We'll also have this room class. So it has a few attributes like the positions that are covered with rock, the tower height, and it will also be useful to track the lowest relevant position. And then again, we can do a drop, which is very similar. We just try to do a push and check if that is illegal, then we reset. Otherwise, we keep the push, and then we want to push downwards, and again check if it's if it hits on the floor or the rock. In this case, we end. And update things like the position covered by rock. And in this case, we also do something else. So we will first check if every single X position is covered by rock somewhere. If this is true, then that's a promising candidate that we might be able to remove some of these positions in the set rock covered because they're no longer relevant for the problem. So how do we do, or what do we do for removing unreachable positions? So for example, if we have a position like this, the dots are air, and the axis as well as the number signs would be rock. The very lower positions we can never reach because it's all like a line of rock above us. So they are irrelevant, so we can remove them. So what we do is we want to get all these positions marked with an X. Those we need to keep because they're kind of at the border. And all the other ones we can delete or ignore. So for that, we will start and initialize a position here, and then always go through all the neighbors. And if the current position is air, we'll again go through all the neighbors and all the neighbors. And this means eventually we will reach all these X positions, and then we can keep them and discard everything else. So in code, we have this above position, which will be here. So the X position, and then we'll put that in a queue, and we keep a set of all the keepers. And while there's still something in the queue, we get rid of an element, and then we check if it's out. If the element is outside, we continue. We don't want to consider that. Otherwise, we add the position to the keepers. Then we check if the position is covered by rock. Then we again continue. Then we check if the position is too high. Then we also continue, and otherwise we will enqueue all the neighbors. So we go through all the. We reuse push there conveniently, so we go through all the pushes in all 4 directions and create the corresponding neighbor. And then we check if the neighbor is not in keepers, that means we haven't processed it yet. We add the neighbor to the queue. And that way we'll eventually get all these X positions as well as a bit of air. And then in order to get the new set of rock covered positions, we just go through all the positions in the keepers and also check if they're covered by rock. Okay, with that we can update the rock covered, which we need to keep track of, and we'll also update the lowest relevant position accordingly. And then that's already quite useful to solve the problem. So how do you do that? We define our push iterator depending on by giving it the input. We'll initialize the room, and we'll also keep track of some saved states. As I said, there's like a lot of iterations, so we need to find some part where it starts repeating. For that we save states every now and then we hope that eventually we'll arrive at the same state, and then we can do some maths in order to figure out how high the tower will be at the end instead of going through all the iterations manually. So again, we'll have a drop number, and we'll keep increasing that until we reach the highest number of rocks. And then we initialize a rock by giving it the corresponding left edge, right edge, and index. Then we will drop the rock. And then we will check every now and then, we will roll over. And if that's the case, we will save the current state. So what's part of the state? We need to keep track of the rocks which will be covered. And that's another reason why we delete all the rock covered positions that we don't need. So this state is as small as possible, and it's likely that we find another state that has the same positions covered by rock. So in order to save that, we will subtract the lowest relevant position, because that's just a thing as we add something, and if it repeats higher up, we'll hope that the formation will be the same, but the position itself can vary by a constant. We'll also need to keep track of the rock shapes which we dropped last, or which we drop next. We can just do this by taking the drop number and taking it modulo 5 for the length of the rock shape. Okay, so if you have not saved the state yet, we will save it, we'll reset this rolled over attribute, and we'll continue. Otherwise, we're lucky. We found a state that repeats, so from then on we can do some maths to figure out, or to get much closer to the final tower height, and don't need to keep dropping elements. So do that by considering the saved state and considering the saved drop number and the saved tower height. Then we look at the iteration difference. We will just subtract the saved drop number from the current drop number, and the height difference, where we subtract the saved tower height from the current tower height. And then we will, so because the state repeats, we know that in another so many iterations, it will again repeat and again repeat and again repeat and again repeat. So we don't need to keep dropping rocks. Instead, we can just jump forward. So how often can we jump forward? That will be exactly these calculations. So essentially, we take the number of total drops and divide by the iteration difference. And then we'll increase the drop number by the number of jumps times the iteration difference. We'll increase the tower height by the number of jumps times the height difference. We'll increase the lowest relevant by the same amount. And then we'll also have this set of positions covered by rocks. We'll also increase each of those positions by the number of jumps times the height difference. So that's kind of simulating doing number of jumps times iteration difference iterations. So that will get us much closer to our number of drops iteration. And then afterwards, we'll only do a few more iterations to get to the end. So yeah, we'll also reset this push rolled over, and then we'll just continue with the loop until we will reach this. The drop number will be equal to the number of drops. Okay, that's already it. We can test this part. With a bit of luck, that works out. Amazing. So we see there we jump from drop 85 to this drop number, so we do jump quite a lot of ahead, so it is very useful. And yeah, we can also run it on the proper input. That also gives us the right result, and it takes less than a minute, so it's very doable. And yeah, that is already it for day 17. I hope you enjoyed today's puzzle, and see you around.